So there are two issues I will not address today. We are talking a little bit about algebraic stacks. So the first issue is a set theoretic issue, namely disclaimer. So something I'm not going to do. So the first problem is a set theoretic problem. So usually you need to recite some incantation about you fix a universe or you fix an inclusion of universes or the like. So consider the incantation done. If you want, pretend whenever I say groupoid, it's a small groupoid, that the objects are a set. So this is a very standard disclaimer. There is a second disclaimer which is a bit more serious, which is I will blur the difference between scheme and algebraic space. And the point is, algebraic space, there is if you're interested in algebraic spaces as such, there is a nice booklet by Artin. But basically the idea is you take the definition of scheme that nobody uses as sheaves which are Zariski locally affine, and when you say see Zariski you put et al. So they can also be viewed as locally ringed spaces, but with the condition that they don't have a Zariski open cover which is affine, but only an et al. One. So the typical, in fact the only example of algebraic space I know is, the following. You take A1 and you quotient it by the relation that t is equivalent to minus t if t is not 0. Now you may say this is a stupid equivalence relation because of course if t equals 0 this is the obvious. But the point is that as a set, this quotient, let me call this u, of course this has a map to A1 with coordinate s, which is equal to t squared, which is 1 to 1. But this is only an isomorphism away from 0, because after all if t is non-zero you are just taking the quotient, but at 0 this is ramified. So the point is, if in other words the map from A1 with coordinate t to here, you declare it to be et al. Everywhere. So the best drawing I can do is not so good because I cannot draw the complex numbers. So I will just draw the real numbers. So what you should think is assume you are over the reals and you glue t is equivalent to minus t for t, say, bigger than epsilon, and then you get something done like this. And then you make the limit as epsilon goes to 0. And if you think that this is something Artin dreamed after eating something which didn't agree with him, this was my first feeling. But it turns out that this kind of objects, which are topological spaces with a sheaf of rings, but have only et al. Charts which are affine. So where do they come out in nature? Well, many ways, but if you are Italian, you are educated into thinking that the greatest thing done for mankind has been the study of moduli of surfaces of general type. And if you take the moduli of surfaces of general type and you work with a canonical model, so contracting the -2 curves, you get a nice scheme. well, or the Ling-Mumford stack, but anyway, you don't have this weirdness. And this thing happens when you take the non-singular model. So this is a kind of the moral reason why in the end working with a minimal non-singular model for algebraic surfaces is not a good idea, because you get precisely this kind of weirdos. So even if your surfaces have no non-trivial automorphism, so the moduli space is a space, you still get that it is an algebraic space and it has these things around. Sorry? This means A1 with coordinate t and this is A1 with coordinate s. You know, I just want to distinguish it's two different A1s. So I typically write, when I have coordinates into something, I tend to write them nearby so that I don't forget who's who. Sorry? Yes. Say it again? No, this is not an anti-map because U is a quotient. U is the quotient. So this is 2 to 1 away from 0. So the idea is precisely what we said, that you are gluing everywhere, but not, it's kind of weird. As I said, it becomes natural once you work with moduli problems, and then this thing pops up by itself. Anyway, so what I will do is I will pretend that all algebraic spaces are schemes. In fact, when people gave you the definition of scheme, they could have done something more and given you the definition of algebraic space. It's not terribly different. And anyway, you don't want to use the definition of scheme, and you don't want to use the definition of algebraic space either. So this is the disclaimer. So the things that I should be saying if I wanted to be completely precise, and I will not do either. And instead, I have a small warm-up exercise which is as follows. So assume this is an exercise back to our problem of why going from the derived, why if you want to work with a derived category of complexes with only two elements, non-zero, this leads you naturally to work with groupoids. So let D from B to A be a homomorphism of abelian groups. And define A over B to be the groupoid whose objects are A, and such that the morphism from A to A twiddle are the B in B such that A twiddle is A plus D of B. Let me call it also X. Then this is a group. So this is a groupoid because, of course, if B is a morphism from A to A tilde, minus B is the corresponding inverse, and the composition is just the sum in B. Here, composition is the sum of elements in B. So in particular, I have a functor, which I can call multiplication, just to distinguish it from the sum, which on objects, it's just the sum. And the same on morphisms, and also on morphism. And what you can check is that this multiplication is strictly associative and commutative. And by strictly, I mean, for instance, for commutativity, strictly commutative means that if I here invert the factors, this is really, this functor here is this composition, is equal. It's not just equivalent, but it is equal. So this is a strictly commutative. So in other words, what you can check is that A over B is an abelian group object in the category of groupoids. Notice that groupoids usually I want to view as a two categories, so I to consider also equivalences. But if I stick to groupoids and functors, then this is just a abelian group object. And now, of course, you can keep doing exercises. For instance, you can check that given a commutative diagram, so remember, this is a morphism in the derived category of abelian groups. This induces a functor from which respects multiplication. So in other words, to a morphism in the category of complexes, you associate a morphism in the category of abelian groups inside groupoids. So far, I'm viewing these morphisms as a category and these objects also as a category, but of course each of them has a two-category structure. So here it makes sense to say that two morphisms are homotopic, and here it makes sense to say that two functors are equivalent. And then the other easy exercise is that if f and g from B1 to are morphisms, as in here. So it means that there is an FA and an FB, which makes the diagram commute, and the same as G. And H from A1 to B2 is a homotopy. Then H induces a natural equivalence between the associated functors. And finally, such an F is a quasi-isomorphism. This means, remember, that induces an isomorphism on both cokernels and kernels. This is equivalent to saying that the corresponding functor is an equivalence of groupoids. And in fact, you can reverse every arrow. So every abelian groupoid object, abelian group object in the category of groupoids has this form. Every morphism which respects a multiplication comes from such a commutative diagram, and every homotopy comes from a homotopy. And well, here I already said it's an if and only if. So in other words, if we are interested working with a category of complexes as a simplicial category, which means we want to remember the whole structure. We have chain maps, we have homotopies and higher homotopies. This a priori is a simplicial category. You have infinite order homotopes among homotopes among homotopes. But if you insist that your complexes have only 2 degrees, the same fixed 1 near each other degrees which are non-zero, then your a priori simplicial category is actually a 2 category. Because between, if we want to understand complexes of length 2, so with 2 elements, whether it's length 2 or 1 depends on how you count, then it's the same as understanding certain kind of groupoids. Or if you want to do it, if you want sheaves of something, then you have to do sheaves of groupoids, and sheaves of groupoids are called stacks. So this is kind of the motivation to what is to come. So now we come to the definition of algebraic stack. And again, I will not give the definition with all the details. I will just give some highlights and some examples. So remember that you can view, remember we want that a scheme is generalized into an algebraic stack by taking the definition. In the definition you take wherever you see a set, you put groupoid, and wherever you see open, you put, well, either étal morphism, and this defines the Lin-Mumford algebraic stack, or smooth morphism, and this defines what I will call just algebraic stacks, but this is the Artin case. And if you're familiar with algebraic geometry, you wonder whether it should be a third one with FP flat something, and the answer is yeah, there could be, but Artin has proven you still get the same. So changing smooth to FPPF or FPQC, which are the whatever they mean, wouldn't change, would still give Artin stacks. So there is no need to, because you don't get anything more general. So, of course, in the definition of scheme, where do you see set and where do you see open? And so what is usually done is to, so I'm not going to write this down, but rather what I'm going to insist is that schemes are a category and algebraic stacks are 2 categories, in the sense that if x and y are schemes, then the morphisms from x to y is a set, and if x and y are algebraic stacks, then the morphisms from x to y are a groupoid. So how do we, and I want that there is an inclusion, so that this is a generalization. So remember, I view each set as a groupoid. This I view it as, can also be seen as a groupoid where the only morphisms are the identities. So how do I do this translation? So one possibility is if you have a geometric background, the way I morally think of schemes of finite type over the complex numbers, it's the same way I look at varieties. So I have a set of points, of complex points, and then on these points I have a topology and I have charts, etc. So in a way, what you would, the typical case, if you have X, say of finite type over C, then certainly in particular you have X of C, which is a set. And in some sense, this set already contains a lot of information, and you put on it a topology, and then you put a sheaf. And here, if you have an X of finite type over C, now I told you what the recipe is. X of C will not be a set, but it will be a groupoid. And of course, your question is, how do I give a topology on a groupoid? And I don't really need a whole topology. What I really need is charts. So one thing, when you do the definition of manifold, you start with a topological space, and then you get the charts from opens in Rn, and then you have the compatibilities. But of course, one of the first things you realize, whether this is done explicitly or implicitly, is that you can just give the set and the charts, and then you just have to be a little bit more careful on what compatibility means. So in some sense, you don't really have to put the topology and the set, so long as you understand reasonably well what you're doing on the charts. Okay? So here, what you could say is that, that you are given UI affine schemes and UI to X, and here I will view schemes as having only the complex valued points. So let's simplify things such that UI fiber product Uj, so the one point here and one point, the pairs of points with the same image, is just, this is a map of sets, is naturally open. It's just open embedding. And then there is a compatibility, what happens if you take I, j, and k, which I will not write down. So here what you do is, and of course you want that the whole of X is covered by this. So this UI, so if you call them Fi, you ask that X is the union of Fi of UI. So what is the corresponding thing for stacks? So for algebraic stacks, you ask that there exists UI, so where UI affine schemes. And now what is this? This, remember, this has to be seen as a functor. So this is a set, but this is a groupoid. So if you want, it's a map to the objects. That's what a functor from a set to a groupoid is. But now, such that, well, first of all, you want that the disjoint union of the UI to X be essentially surjective. I mean, this is a groupoid, it's a category. So usually asking that things are surjective on categories is not a very good idea. What you want is that this object here is isomorphic to something. Each point is isomorphic to a point in the image. You want a definition which will not change. You see, when you give the definition of manifold, you want that if you replace X by another set which is bijective, you will still get an induced structure. And on groupoids, the natural notion that you want to change and nothing changes is you want to replace a groupoid by an equivalent one. So even if you start with something is surjective, when you pass to something equivalent, it will no longer be surjective. But you want that it's essentially surjective. And then you want, and such that, and now for all I and j, you take this fiber product, but this is a fiber product as a category. And this category is automatically a set. It's what is called the rigid category. So what is, so the objects here are pairs, UI, are triples, UI, UJ, and phi, where UI is in UI, UJ is in UJ, and phi is an isomorphism. So just two elements which have isomorphic images. And then you have to say what are, and the morphisms are only that there are no morphisms. The morphisms are just the identities in this case. And what you want is that this set, in a natural sense, that this a priori is a set, but it's a set with the natural maps to, say, each UI and UJ. And you want that this is a scheme, and that this morphism is either étale or smooth, depending. I told you that I wanted to either have étale or smooth, so you put it in here. And the general definition is the same. So this is in the case of finite type over the complex numbers, and otherwise you have to do it for every affine scheme. You have to do it functorially, the same picture. So, but this is the basic idea. Yes, exactly. If you know what it means, so another way to say it is if you call U the disjoint union of all the UI, which is a scheme, maybe not a finite type, and you call, let me call it X1, X0, and you call X1 the disjoint union of all UI cross Uj. And in this case, the case where I is equal j has to be included, because now this fiber product will no longer be Ui. Well, okay, so there are two ways to define it. So one possibility is to say that this is a groupoid in the sense that these are the objects and these are the morphisms. And another way is to say that this is a generalized equivalence relation. You can call this U and you can call this R, and you can, either way, you have that these two maps give you a map from two maps from x1 to x0. One is given by the first coordinate, the other is given by the second coordinate. Or if you want, they give you a map. And this is a generalized equivalence relation, in that when you have something which goes from ui to uj and something which goes from uj to uk, then you have a composition. And this is the famous. So what you want, if you want, is that you require that this is a étale or smooth groupoid. And étale or smooth means these two maps are étale or smooth in the category of schemes. It means you take the definition of groupoid where you say, you assume the objects are a set and the morphisms are a set, and you write the whole definition of groupoid as maps and commutative diagrams. Last I heard it was like 4 maps and about 10 commutative diagrams, so you don't want to really do it unless you are writing a textbook. But basically what you get is then the quotient. So this object here completely determines the quotient stack. Yes? What was, sorry? Yes. what I said, if X is a scheme of finite type over C, okay, what I'm trying to do is find a way to describe it. There are several ways. And one possible way is to say, something which I don't know why it is never written in, or rarely written in algebraic geometry books, that you can describe it the way you do manifolds with charts. Okay, so you start with a set and you put on it, when you define manifolds, usual definition is you have a set, you put a topology, and then you put charts. But what I claim is that you are all familiar with cases where you start with a set and you directly put the charts and you use the charts to define the topology. And this is what I'm doing here. Yes? No, it isn't, but it becomes a topological space if I insist that this is an open embedding. So what I'm saying is that this has a map to ui and a map to uj, and what I ask is that this is injective, so this gives this one not only a topological space structure but a scheme structure as an open subscheme of this. And it also gives it a scheme structure as an open subscheme of that, and I insist that they are the same. No, that they're not, no. This is, it's either the same or not. So the point, okay, maybe there is an isomorphism, but at least the topology is the same, and the scheme structure is isomorphic, and then when you do it 3 times, then it is it all commutes. Okay, so the point is I tend to forget that schemes can be non-reduced. And then if I think of the scheme, on a reduced scheme, the scheme structure is just given by giving the topology, and then for every open subset, describing which functions to C are regular and which not. So in that sense, it's really the same, because they give the same regular functions. Of course, since schemes may non-reduce, you have definitely a point, and you have to choose an isomorphism and then ask for a cocycle. And so what you have here is that this is really open, just Zariski open. And in particular, this will imply that this map is also injective and will end up being an open embedding. But it kind of comes out of the picture. And here, so let me give you the key example. So as I told you, writing down what is such an internal groupoid is very complicated and very unpleasant, but there is a special case that is very easy to do if V is a scheme over a base scheme. Let me start with B, a scheme, and let V be a B scheme and G a group scheme over B. And now and assume that this is smooth over B. In many cases this will be true for many interesting groups. In particular, if B is a spec C, then definitely every group scheme will be smooth. And now I want to tell you, so in particular in this case, I can consider G cross B. This has 2 maps to B. Sorry, G cross over B with V has 2 maps to V. One is the action, is the second projection, and the other one, sorry. And now I'm assuming that G acts on V. And what I claim is that this defines me precisely such a generalized equivalence relation. And what I want is, I want to produce what is the quotient. What is the corresponding quotient stack? And to describe what it is, now I will go back. So so far this was an informal introduction, but usually what you do, this is not the way you define algebraic stacks, because as I said, if you instead of want to do it over the complex numbers and everything finite type, you want to work over like with schemes, over an arbitrary field, you don't start with points. Well, there's the usual definition, but there is another approach, which is what I think is called the functor of points, which is a very old idea, except that it's not in Hartron. It took me a while to figure out it existed. So a scheme is determined up to canonical isomorphism by its functor of points. So here what I view is that if X is a scheme, you define a functor. It's you can of course you have the Yoneda functor, that this is kind of obvious in any category. And the functor of points associated points is just Hx, but restricted to affine schemes. Or if you want, this is just rings. And the point is that, of course, not every such functor is a scheme, but if it is a scheme, what is called is representable, then the scheme which it represents is unique up to canonical isomorphism. And a necessary condition, this functor of points in particular, is a sheaf in the, say, étale topology, in that étale descent holds. And so the way this is the informal definition of algebraic stack. This is how you go about, or at least that's how I go about understanding whether something should be an algebraic stack. I wonder whether there is a set of a natural underlying groupoid, whether the things I want to parameterize, when is a groupoid essentially, when is a groupoid equivalent to a set? And the answer is a groupoid is equivalent to a set as a category, if and only if it is rigid. So it doesn't mean that all the morphisms are the identity, but it means that all the automorphisms are identities. And this in turn is equivalent to the fact that when you have two objects, either they are isomorphic or they are not. But if there is an isomorphism, it's unique. So the idea is whenever you have a moduli problem which comes as quotienting with an up to isomorphism, what you should do is sit down and figure out, is this isomorphism unique when it exists? If it's unique, you can forget about it and just work with it. Expect to have a scheme, or as I said, maybe an algebraic space. But if it's not unique, and in particular if the automorphism group changes, some groups have non-trivial, some points have non-trivial automorphism and some don't, then usually you are really looking at an algebraic stack. And if you can really try hard and pretend it's a scheme, it will not have nice properties. So the point I'm trying to make is that this viewpoint, to look at the points, is not what you use for the formal definition, but it's what you use when you, as an algebraic geometer, have a moduli problem, and you ask yourself, is there a stack here which I should be aware of? So it's how you realize that stacks exist. So, and here, algebraic stacks are pseudo-functors from, again, rings. Two groupoids. And the way this is a pseudo-functor means it has, and which are stacks in the étale topology. Which, well, it's not my fault. Sheaves of groupoids. This is an unfortunate, I wasn't even born when the name Champ was chosen. Champ is a sheaf of group, so the name stack was chosen later. I was born, but I didn't speak English, or I didn't speak. Anyway, so the point is, this is the name. For some reason, when something is a sheaf of groupoids, you don't call it sheaf. You call it stack. Or if you're speaking French, which maybe you should, is called champ. Yeah, okay. But the nice, I've never seen any, of course you can think of many other definitions for, it's just this is the definition, your gut feeling is that this is a sheaf of groupoids. Of course you can't think of other stuff and ask yourself. Also because the typical thing is then you wonder, actually in the end, this is not even the right thing, and there is one more cheating going on, but I tell you tomorrow about that, because you can't have too much confusion in one go. So which are stacks in that they can glue. And so the point, no, the problem is, there's another cheating, there's something else I'm hiding under a carpet. Some other disclaimer I should have, and I don't, because nobody does in the literature, but I will tell you all the same, but tomorrow. So they glue as well as groupoid glue, so it means you have local objects, you have to choose isomorphism on the intersection, and then you have to ask cocycle. And it's functorial in the sense that if you have it on a scheme, you pull back and then you pull back again. It's not the same, but it's canonically isomorphic, and if you pull back 3 times, this isomorphism commute. So again, you can write very large diagrams, but I prefer not to. And instead, I want to give you a few key examples. Because basically there are not so many examples necessary. Yes? Okay, that's the part I didn't want to say. So the point is, usually, let me give you an example and then I'll go back to what you just said. So example 1, and example 1 is chosen because this is the example which was the motivation for defining algebraic stack. So this is due to the linear Mumford. You fix a G at least 2, and you define Mg from schemes to groupoids, schemes of. Notice that a priori algebraic stacks are defined on affine schemes, but in practice eventually they are in these big 2 categories with scheme also are. So most of the time it's actually easier to define them on all schemes. So if you want consistency, you just pretend that all the schemes here are affine. So what do? I say that Mg of S, so I have to give you a groupoid. The objects are phi from C to S, smooth projective morphism such that the fibers are connected genus G curves. And let me assume my schemes are affine here, so I don't have to worry about all the many non-equivalent definition of projective. If this, sorry? Yes. Sorry, geometric fibers. I still think of points as closed points, but of course the geometric fibers. And now I have to tell you what the morphisms are from pi C to S to pi 1 C1 to S. These are the F from C to C1 isomorphisms as schemes such that pi is pi 1 composed F. So how is this a functor? And now we will go back to the cheating and to the question he had asked. So how do you pull back? Well, if you have S tritle to S, so this is an epsilon, and you have a pi from C over S, what is its pullback? And the answer is, well, this is C times S as tritle with its natural map to S tritle. And the point is that if you read in Hartshorne, this isn't really a well-defined scheme, but it's only a scheme well-defined up to canonical isomorphism. So what you could do is instead view all such maps for S varying and all such diagrams, all fiber product diagrams as a category. So the objects are these and the morphism are the Cartesian diagrams. And then you have a forgetful morphism to schemes, which is given by you take such a thing and you just keep the target, the base. And this is what is called a category fibered in groupoids. And basically the difference between a pseudo-functor and the category fibered in groupoids is that in the category fibered in groupoids you have chosen a fiber product, while, in the pseudo-functor for each morphism and each object you choose a fiber product, and in the fiber category approach you keep agnostic, you say, okay, there exists a fiber product. So in some sense the fiber category is more natural. On the other hand, when you want to write the stack condition, you never want to do it using the language of fiber categories. You always want to assume that you have chosen fiber products, that you have chosen pullbacks. So yes, it's canonically. Yes, that's what a pseudo-functor is. So that is the easy part. So this is all kind of implicit. That's why there is a pseudo, because it's not a this is a category, and of course this is also a category in an obvious sense, but this is not a functor between the underlying categories, but there is this fact that when you pull back twice, then you get. And the point is, however, that if you view schemes as functor, then the fiber product is canonical, because the fiber product of sets is a well-defined fiber product. It's not up to bijection or whatever.
That's where I was saying. Even with this fiber product of sets, it would be a pseudo-functor.
Yes, it is in some sense still a pseudo-functor in that it's not a functor. It's only that it's canonically bijective.
Two sets.
Yes.
Actually a subset of the product.
Exactly. Yeah. That it's not really a functor. Yeah.
So I'm saying that just for my own head. It's nothing to do with schemes. It's already at the level of sets.
it's already at the level of sets. In fact, I insist that in my opinion, when I think of a fiber product of schemes, I always think as the fiber product of the underlying sets, and then I give it whatever topology and sheaf and whatever I have to put on it. But all the problems come from the set theory already. So it's not the geometry which creates trouble with us. It's just that, and in fact, in a set languages, so in a categorical languages, this language of fiber categories is much more natural. The problem is that when you want to put the geometry into the mixture and ask this and put the stack condition, writing the stack condition in terms of the fiber category is unpleasant. Let me put it this way. And so what everybody does is they give the definition with fiber categories and then start talking about pullback, pretend we have chosen one. So that goes back to my original incantation, which was, assume we have a sequence of universes, because basically what the incantation tells you is that you have a nuclear powered axiom of choice. And so, what you know is that there exists a fiber product for every object and every morphism, and so you just choose one already. And then you are kind of done. Anyway, so what I want is that you don't focus on the technical details and instead notice that this is actually a functor. So that the fact that this is smooth implies that this is smooth because smooth is stable under base change, and the same for projective, and of course the geometric fibers are the geometric fibers, so that's why it's called fiber product. Okay, so so if I want to understand this geometrically, so what would be if I work now, say, over the complex numbers? So what are the objects of Mg of C? And I should write spec C, but I'm always identifying. Well, these are, so what is this? As a groupoid, this is given by complex, non-singular, complex projective curves and of genus G and the isomorphisms among them. So this is very clearly a groupoid. So is it a rigid groupoid? And the answer is no. It's never a rigid groupoid, because for any genus you can find a curve of genus G which has non-trivial automorphisms. But of course, you can also consider M0G inside Mg to be, so for any S, you let M0 Mg of S be the full subcategory such that the geometric fibers are rigid in the sense that their automorphism group is only the identity. I mean, this is definitely exists, right? I mean, I have put this definition. It's a further condition. If you put condition of the fibers, they will be invariant under base change. So this is also a stack. So what happens if I have a morphism from S to Mg? And I have the natural map from M0G to Mg, what happens when I do the fiber product? What do I get here? So what I want to know is, given any other S triddle to S and here, so what do I have to put here? So my question is, assume I have an S triddle so S to Mg, this corresponds to a family C over S. S twiddle to M0G corresponds to a family C twiddle to S twiddle. And then what I want is fiber product. Remember, this is a groupoid. So fiber product means that I have given an isomorphism alpha, and then I have a map from S twiddle to S. Let me call it epsilon. So what I want is I want to pull back from here and pull back from here and have an isomorphism of the induced thing. So I have to have an isomorphism from C twiddle to epsilon pullback of C. So what does this mean? This means as fibered object on S twiddle. Well, this means that since these fibers are rigid, these fibers are also rigid. So certainly epsilon of S twiddle is contained in S0, which is the S geometric point in S, such that the automorphism group of CS is just identity. And the point is that this is open. I mean, in general, if I just give a bunch of geometric points, they are just a bunch of geometric points, but if they determine an open subscheme, then this open subscheme is unique. And it's an easy exercise to check that this is actually open, and conversely. So what you can do as an exercise is show that indeed S0 is this fiber product. Sorry? I didn't, well, in general, okay, so in particular, what this tells me is that the morphism from M0G to Mg is an open embedding. By definition, this means that whenever I base change with a scheme, I get an open embedding. And as was remarked, if G is equal to, then M0G is actually empty. And it turns out that, of course, M0G of S is more or less by definition, actually this is a good exercise, show that M0G of S is a rigid groupoid for all scheme S. So this is, let me give you an idea. If you have, what you have to do is you have to take any object and prove that the only automorphism is the identity. And this automorphism must map fiber to fibers. So on each fiber, it has to be the identity. So if S is reduced, this basically finishes it. And if S is non-reduced, you have a little argument to do, but it's not a very difficult argument. So since this is a rigid groupoid, I can take its associated set of equivalence classes, and I can view it as a set by taking equivalence classes. And indeed, the corresponding functor to sets is representable, is a quasi-projective scheme. So this is it's a smooth quasi-projective scheme of dimension 3G minus 3, except it's empty if G is equal to 2. But you know, the empty set is still smooth and quasi-projective. It's just not a very interesting set. So as the mod G for V a scheme and G a group scheme. And this is actually an absolute construction. It's over spec Z. So this is very rare that you get stuff which works without trouble over spec Z. So what you do is basically, so I have to find you a V and a G. So what does it mean to say that it's the quotient stack? It basically means, remember that you will have, you have to produce a principal G bundle over Mg, which is a scheme. So something you have to add additional structure such that now the objects become rigid. So what you do is you write V as, let me write it first, as on the set level. So let me show you first that I can write Mg of C as V of C modulo G of C, and as a stack as groupoid quotient. So this is the groupoid where the objects are element here, and the morphisms are group objects which send one to the other. So what I want to do is I want to write V of C as to be the data. So let me choose something natural. Let C be an element of Mg of C, any curve, hyperelliptic or not. And then I call L C Kc to the 3. And I could choose any number higher than 3. The point I choose 3 is that this is always very ample. Most of the time Kc is also very ample, but not always. So I go as high enough that this is ample, and moreover, sorry? G was at least 2, right? I'm still, I mean, once I say something, it's that. Otherwise, this is much, it's not, well, we'll say one moment what happens if your G is not at least 2. So if you take Kc at a tensor 3, this has also the nice property that H1 of LC is 0, which means you know what H0 is. I mean, you can write a formula, but let me call just n plus 1 the dimension of LC. This n plus 1 it depends only on G. And let me call D the degree of L. So both n and D only depend on G and on nothing else. And then what I do is I define V of C to be the set of data C V0 Vn such that C is a curve as before, and V0 Vn is a basis of H0 of CLC. And this is as, I want to define a category, so let me say that these are the objects, and what are the morphisms from C VI to C twiddle VI twiddle. Well, these are the set of phi from CI to from C to C twiddle. There is a canonical isomorphism between the pullback of LC twiddle and LC. So in this isomorphism, I require that the pullback of VI is of VI twiddle is VI for all I. And of course, this is a rigid groupoid. It's kind of obvious because if you have an isomorphism which fixes the basis, then, so what are, if I have one curve, two elements here which have the same image, in how many ways can I do the fiber product? And of course the answer is I can always change. So what is, if I look at the map from this, if I look at this morphism of functor from V to mg, and I fix a point here, which means I take a specific curve. Well, this fiber is a principal GLN bundle, because it's the set of all bases of vector space or GLN plus 1 bundle. It's the set. So what happens, what you can prove is that this V of C is quasi-projective. Basically, it's this V of C, now you can make a scheme theoretic version. So it's V of S is C of S, and then you have to take the basis of the fiber bundle, which is the total push forward, and so on. And but what you can do, just at let me be informal and work just at the point level. If I now take this up to isomorphism, this is naturally a scheme. Sorry? It's a groupoid, but I can associate it with a set because it's a rigid groupoid. So I don't lose any information if I pass to the isomorphism classes. And I have a natural map from V to the Hilbert scheme of Pn, which sends a curve to the image in Pn given by this explicit basis. And this map here, if you view this as a set, this has as image a U, which is open in a Hilbert scheme. So you have a Hilbert scheme, they all have the same Hilbert polynomial, which is determined by the genus and the degree, and it's a usual formula. So this is Hilbert P, and P is dt plus 1 minus g. I mean the Hilbert polynomial of a curve of degree d and genus g. And this is actually open because the locus, if you have a fat family of curves, the locus where the curves are non-singular, sorry, this is not open, no, sorry, this is locally closed. It's locally closed because the fibers, you are insisting, there is an open locus where the curves are non-singular, and then on each of these curves, you have that O of 1 gives you a line bundle of degree d. And then you have to look at the locus where this line bundle is actually Kc to the tensor 3. And to do this, you have to take the inverse image of a point in the Picard, relative Picard variety. So this is, you have a section of the relative Picard variety, which is given by choosing for each C this line bundle, and you fiber product. So it has a naturally locally closed structure, and this thing here is just a C-star bundle. Because the smooth and yes, there is an open of the smooth ones, and in the open of the smooth ones there is a natural closed, which is where this line bundle is the one I say it is. In fact, the open is non-singular and the closed is a non-singular subvariety of codimension G. Because of course, once you have fixed this high degree, every line bundle has H1 equals 0, so they all have the same number of sections. So you could have taken any of them, but the point is I've chosen a specific one. And so what you get, yeah, I will get to that. So, anyway, the point is this is just a C-star bundle, so this is a scheme, so this is a scheme. And then what you have is that this Mg can be written as at least a set, as a set of complex valued point is the stack quotient of V by GL n plus 1. And then you can do these in families, you can do it over spec Z, and you still get this construction. So notice, however, in some sense, I could have said, okay, it's as well to define quotient stacks because this scheme, this stack is a quotient stack. However, let me insist that in some sense this is a rather artificial construction. So the natural definition is this one. And in particular, here I chose 3, but I could have chosen 4 or 5 or 6. So the key idea is that this is a stack which kind of exists by itself, and then you can represent it as a quotient stack. But in some sense, you can do it when you need to, but you don't have to. In some sense, a natural way to think of it is this one. And the other question was, which was actually a nice question, what happens if G is smaller than 2? Well, there are several things that happen, of course. One thing that happens is that you no longer have a canonical posit ample line bundle. For instance, if genus is 1, you don't have a canonical thing. But the other thing is now that, so what happens is this Mg is a Deligne-Mumford algebraic stack. And here I have G is at least 2. So notice that the families we have defined so far aren't at all. They are smooth because the fiber is G, which is a big thing. But what you can do is you can find, the point is that, let me not go into detail, but you can find families C over S such that the morphism S to Mg is surjective and et al. So what do I mean by saying it's surjective and et al? I mean that, i.e., for any other morphism S1 to Mg, the fiber product is surjective and et al. And the key point here for this to be possible, and this is essentially an equivalence, so you have that an algebraic stack, say, again, let me assume that it's a finite type over a field. It's true more with some caveat in a more general way, but let me stay in the case I understand. And let me insist that this is maybe just locally of finite type over a field, is Deligne-Mumford, so it has these et al. Charts instead of smooth charts, even only if for every geometric point so a geometric point is an object over an algebraically closed field, but over an algebraically closed field I still have a groupoid, and what I have is that automorphism of X. Notice that this is a scheme because there is a general assumption I have is that for any morphism from a scheme, the fiber product, so the algebraic stack big X, So the fiber product here is the automorphism, because this is one object, it's always the same. Actually, let me be precise, this is spec K, this is spec K, and this is X. So remember, the fiber product means that you take the two objects and you have to give an isomorphism. So here the object, there's only one, so the fiber product is this, and this is automatically, in fact, in general, an algebraic space, although in this case it actually is a scheme. And what you want is that this here is et al. So for if K is in characteristic 0, et al. Just means that it has a relative dimension 0. It has dimension 0. And if K has positive characteristic, you can get stuff where this group is proper, but it's not et al. And it actually happens. But the point is that in the case of MG, the tangent to the automorphisms, this is something one can easily compute. It's tangents to morphisms. Morphisms are an open substack. Morphisms from X to Y are an open subscheme of the Hilbert scheme of the product. So this is just a tangent to a Hilbert scheme. And this tangent is H0 of CTC. And this is 0 because TC has negative degree. So even in characteristic P, this is 0. And so this is automatically et al. And that is all we need to check. So what happens is typically the typical object, so this is a well-behaved stack. It's a Deligne-Mumford stack of finite type. Why is it of finite type? Because I have found one finite type, quasi-projective scheme which maps on it surjectively. So this is not just locally finite type, but it's finite type.
So for that you require the quotient picture, right?
Say it again?
To see this, you do require...
I think it helps. You can do something more... You don't need the quotient. What you...
That is the RSS that exists, that's all.
So what I could do is I could work with an open subscheme of some Hilbert scheme where I'm sure that all these curves are.
You don't need the quotient.
You don't need the quotient.
There's something with the charge.
Exactly. So the point is that, so the point is that now you can do something completely crazy and look at you can look at the stack MG, and this time G any non-negative number, and the definition is as before, but you take P from C to S, and pi is flat projective, and the geometric fibers are connected nodal curves of arithmetic genus G. Sorry? No, this is a very curly M. I haven't put any stability condition, you see? This, sorry, for the note takers, this is my interpretation of this letter. I'm sorry, this is as good as I can draw it. So it's, please imagine it written by a German. Anyway, and with the same isomorphisms as before. And pull back. And I want to show you that MG is an algebraic stack locally of finite type actually again over spec Z, but let me just work over C. It is also true over spec Z, but I don't want to prove this. I don't require anything. I just insist that it's nodal. In a moment, we'll see that I could even go weaker than that. So I want to prove, how do I prove that it is locally of finite type? I have to prove that I can find for every point a scheme and a morphism such that this is a smooth open map and this point is in the image. And smooth open means whenever I fiber product, I get a smooth open. So let me fix C such a curve. C, an object, a C valued point. And I now play the same trick. I choose L, a line bundle on C, which is sufficiently ample such that L is very ample and H1 of CLC, L is 0. I mean, I can't find such an L. And I choose a basis of, choose basis of H0 CL. So this gives me a closed embedding of C into some Pn of some degree D. And now what I do is I take U inside the Hilbert scheme P of Pn, where P is as before, P is deg L times T plus 1 minus G. So, and U is now the open subscheme parametrizing nodal genus G curves with H1 genus G curves CU, because each curve comes from one point, which H1 CU of 1 is 0. So even this condition is open because of cohomology and base change and the fact that these are curves. So H2 certainly base changes with anything because it's 0. So it is very much the same idea. So this is definitely an open condition. And did I write? Yes, it's nodal. So certainly the universal family gives me a morphism from U to Mg, which has this point in the image or in the central image. So how do I prove that this is smooth? And the answer is, let me just explain to you why this is smooth. The point is that the first order deformations of C are given by x1 omega C OC, and since C is LCI, I have an exit sequence as you know, the one we have been using all the time. So in the book of Hartshorne, you learn that this sequence is exact when Pn and C are smooth. But it's actually still exact if Pn is smooth and the thing you're putting it in is LCI. And this is locally free. What goes wrong is that this is no longer locally free, but it doesn't matter. So what you get is you get the tangent space, you get at home omega I mod I squared to OC goes to x1 omega C OC goes to x1 omega Pn restricted to C, OC. So this is the tangent space to the Hilbert scheme, or for any u. Sorry, take a u in u, and this is for any such u. This is true, not necessarily the one I started with. So this is the tangent space at u of the Hilbert scheme, which is also equal to the tangent space of u because u is open. This you can prove, in some sense, this is more or less by definition of first order deformation, this is the tangent to the stack. And this is 0. This is 0 because I have made this assumption. You just use the Euler sequence and dualize. This is H1 of C, TPN restricted to C, and TPN is a quotient of a direct sum of of 1. So if those have no first cohomology, then this one doesn't either. So this is 0, and so you have that this morphism is surjective on, well, you can go on, and what you get is that this is surjective on the tangents and injective on the obstructions, because there are no obstructions, you do a little bit extra computation. And then there is a general theorem in deformation theory that tells you that the map from U to MG is formally smooth. And formally smooth, since you prove that for any other scheme, the fiber product will be a scheme, then you get that the result is that this is smooth. So it's just a little bit more argument in deformation theory. So this is the picture. These are the objects we want to work with. And finally, let me say, I really need 5 more minutes. However, I want to be able, there is one kind of stack I want to be able to construct always. I started to tell you, if I have a scheme and I have a group scheme acting on it, I want to be able to construct the quotient stack, which will be algebraic under good assumption. Typically what you want is that the group scheme is affine over the base. So you don't want to take a point and quotient it by an elliptic curve. This is not good. So there are precise assumptions, but informally it is essentially that you are working with affine schemes. I don't remember if in characteristic P there's something else you have to be careful about. So how?
Sorry, I didn't get the point. You don't want to quotient by an abelian variety.
Yes, I don't want. I definitely don't want quotient by an abelian variety. So but you know, as a stack, the quotient can always be defined. The point is I want something nice that I can have theorems about later. So if B is a base scheme, V is a B scheme, G is a group scheme over B acting on V, then I want to, how do you define a quotient stack? And the problem is that you want something which essentially says that the objects are the morphisms to V, and the morphisms are given by morphism to G, just as before, that these are the objects and these are the maps. However, when you work this all out and you insist that you can define locally and glue using G as the gluing, what happens when you take things which are kind of obvious and you glue it using G? The answer is you get principal bundles. So you can either verify by yourself or believe me that the natural thing to get is to define V over G as an algebraic stack, or let me insist that first it's a stack, from schemes over V to groupoids is defined by V over G of S, which, remember, this just is the morphisms from S to V over G, and this is an op. This is given, I have to give you a category. So I have to give you what are the objects. The objects are P over S, which is a principal G bundle. The objects of these are pairs. First of all, I have a principal G bundle. S is a scheme over B, and G is a group scheme over B, so I can pull it back. If you want here, you can put a GS, but I think we all know what we mean. And P to V, a G equivariant morphism. And the morphisms, so a morphism from PF to P1 F1 is an isomorphism epsilon from P to P1 such that the diagram commutes as G bundles such that F is F1 composed epsilon. So these morphisms are, the set. So you can see that the morphisms are essentially subsets of G, but they are very special. And, G here is any, B is a base scheme, just a fixed base scheme. S, so I fix a base scheme. I want to do this condition relative to a base scheme. S is a B scheme. Yes. Yes, everything is over B here, and then I define this. And the pullback is obvious. If I have a principal bundle, I pull it back and I compose the map. And what you can check, which is a nice exercise, is that if, so I told you that V is a scheme with a G action. A special case of scheme with a G action is it could be a principal G bundle over something. If V with its G action is a principal G bundle over W, then the stack, the groupoid V mod G of S is canonically equivalent to the set morphism from S to W compatibly with pullback. The equivalence is given by you take a map from S to W and you take P to be the pullback of V. So, in some sense, what the stack does is it makes every quotient as if the group were acting freely and properly, discontinuously, or whatever you want. It behaves like every quotient is the basis of a principal bundle. And in fact, the other exercise is you can verify that for any P over S F object in V mod G of S, the diagram P over V to S to V over G. Notice what is this map here? Well, there is a natural map from V to the quotient, which is given by, you take G times V, this is a principal G bundle, and you send it to V in the only G equivariant map, which is just the action. Okay, so this gives you an element from V to Vg, and this is a Cartesian diagram. And in particular, this tells you that all these maps are always surjective and smooth, because I have assumed, actually I didn't assume it, let me assume that this is a smooth group scheme. I don't want to go and discuss what happens is when the group scheme is not smooth. This is Cartesian, and in particular this is really a chart. It's a presentation for my scheme, smooth chart for the scheme, and I get. So this will be the key example we need, and we will put together our original intuition, the one we started with, that if we want to take a derived category of length, just morphisms, it's as good as taking the associated groupoids. And then we will apply it not taking the category of abelian groups, but we will apply it to the category of coherent sheaves on a scheme. And we will go from coherent sheaves to abelian cones by having this geometric picture we had seen at the very beginning, that coherent sheaves have a geometric counterpart. And then we will do this quotient, and what we will define is these abelian cones and abelian cone stacks. That is what we will need to do the general intersection theory. And before I leave, let me tell you one thing I suggest you think about, namely a special case is that if B is a spec C, and for instance G is a nice affine group, for instance GLN, then what G acts on is a B group, and it acts on B in the obvious way. There's only one action, because it's just one point. And what you can do is you can do the quotient B over G. So what is this? If you compute it over a certain S, well, this is just, well, I have to give you a principal G bundle, and then I have to give a G equivariant map, but there's only one map to B, which is the constant. So this is all I have. So in other words, this actually is usually called BG. I cheated here with the choice of letters. And the BG because this object is the stack of all principal bundles. So if you are familiar with topology, you know that there is something called the classifying space, which has a universal principal bundle, and every other bundle is a pullback. And this, in algebraic geometry, instead of finding something which is homotopically equivalent to a point, such that when we act by G we get a bundle, we do this trick that we just take a point and we do the quotient in a different way, so that we get still a universal principal bundle which induces all others. So remember, when you do topology, you are used to the fact that in order to get reasonable things, you have to work up to homotopy. And working up to homotopy means you are really working in a simplicial category, or if you want in a higher category. And this is what we are doing here. So this is really the algebraic geometry counterpart of something that when you do it in topology, at least in Italy, you teach homotopy in the second year of college. It's considered a very elementary concept. But when you do it, this could be something elementary. You could teach this stuff very early. It uses a bit of category theory, but it's very elementary category theory. It's not fancy stuff. And this is just a good way for me to understand what is the classifying space. So in some sense, in algebraic geometry is much more straightforward. You don't take something which is homotopy to a point, just take a point on the nose. Okay, and tomorrow we'll see the rest.